Deformable Gabor feature networks for biomedical image classification. We revisit Gabor filters and introduce a deformable Gabor convolution to expand deep networks interpretability and enable complex spatial variations. As illustrated in the figure, deformable Gabor convolution includes deformable convolutions and adaptive Gabor convolutions that share the same modulation information. The deformable convolutions are endowed with local offset transforms to make the feature sampling locations learnable. The adaptive Gabor convolutions further facilitate the capture of visual properties such as spatial localization and orientation selectivity of the input objects, enhancing the generated deformable Gabor features with various dense transformations. In this manner, the features are learned at deformable sampling locations and with adaptive Gabor convolutions to improve representativeness and robustness to complex objects. Let us review deformable convolution. We use fx and fy to denote the input feature and output feature of the convolution respectively. The difference between deformable convolution and traditional convolution is that deformable convolution further learns a offset delta r at each location to adjust the receptive field of input feature fx on which the convolution is implemented. In our deformable Gabor convolution, both the deformable convolution filters and the Gabor convolution filters are acquired through modulation. C as the convolution filter, SV as the modulation kernel. They are combined through element-wise product operation to obtain D as the deformable convolution filter. Similarly, we obtain adaptive Gabor convolution filter G through the modulation kernel S and the Gabor filter G. Note that modulation SV are shared and learned masks. In this manner, we combine deformable features and Gabor features to enhance representative ability. The new module is lightweight and can easily be implemented with a small number of additional parameters. We first experiment on in-breast dataset. The in-breast dataset is a dataset of mammogram images from women with both breasts or from mastectomy patients. To validate the network's robustness to deformation, we generate a deformable version of the dataset called in-breast deform by sampling 50 images with random scale and rotation for each test sample of the in-breast dataset. We compare DGFN with the baseline networks, including CNN, Gabor convolution networks, denoted as GCN, and deformable convolution networks, denoted as DCN. Different kernel stages indicate different model sizes. Table 2 shows that DGFN outperforms the baseline networks with similar amount of parameters. From Table 3, our designed method achieve better AUC compared with the previous approach on multi-instance learning. We also experiment on NIH chest X-ray 14 dataset, which consists of 112,120 frontal view X-ray images labeled with 14 advanced lung diseases. We divide the compared methods into fine-tune and off-the-shelf based on whether it used additional data for training. Table 4 demonstrates that among the group labeled fine-tune, our DGFN initialized with ImageNet outperforms the others on all 14 pathologies. Among the group labeled off-the-shelf, DGFN performs better on 11 out of 14 pathologies than other methods. Experiments on the CFAR-10 dataset. We generate a noisy version of test set for CFAR-10 called CFAR-10 noise by randomly adding Gaussian noise. We compare CNN, GCN, DCN and DGFN of similar sizes. Results show that the proposed DGFN outperform the baselines on CFAR-10 noise, demonstrating its own superior robustness to random Gaussian noise.